Yes, good afternoon, everybody. Welcome to this session of sustainable construction methods. Today, we'll be seeing this topic foundation. Uh, what is foundation and what are the different loads which come onto the foundation? How do we design a foundation? Let us see that here. See, basically, the foundation rests onto the soil, so we'll have to see what are the different types of soils also because they are related to each other. See, soil is a natural aggregate of mineral grains, loose or moderately cohesive, inorganic or organic in nature, that have the capacity of being separated by means of simple mechanical processes. Simple mechanical processes. Structures are built with soil. As we know, we need structures which are built with soil, like dams. Some of the structures which are built with soil are dams as well as embankments. Structures are built in soil, that is inside the soil. Some structures are built using the soil, and some are built inside, like we pierce it inside. So structural foundations, you can see here, they are footings, they are piles, they are rafts and tunnels. These are the structures which are built in soil. Let us see it here. See, what is now geotechnical engineering is. It is a unique combination of science, experience, judgment, and a passion for understanding the uniqueness and variability of ground conditions resulting from forces of nature. Basically, what happens when this, what how the loads the uh, how the loads are transfer from one element to other element is, first the load from the slab is transferred onto the beams, and from the beams to the columns, and from the columns onto the footings, and this load onto the footing is now transferred onto the soil. So basically we need to soil these this total loads coming from these different elements. How can that be resisted by the soil? Even this is part of this study. It is very much needed here. If the soil is not able to resist this load, and the soil is not that good, then there will be problem of settlement of the structure also. So it is very important, we need to know the properties of soil also. What is the bearing capacity of soil, whether it can bear the loads or no, that has to be studied beforehand. It is the art of determining the properties of unseen and variable materials to provide a facility that perform as expected at acceptable level of risk and at an optional cost. Basically, this is the we have to know the different types of properties that soil contains. If the properties, if the properties are not up to the requirement of withstanding the loads, then we'll have to go for some treatments to increase the load bearing capacity of the soil. So even this is needed uh, well in advance. Let us see, geotechnical engineering involves investigation and engineering evaluation of earth materials, including soil, rock, groundwater, and man-made materials, and the system's structural foundation and other civil engineering works. So basically, all these are related to geotechnical engineering, because we need to know what are the different materials inside the earth. Also, sometimes you come across some rock particles also inside. Sometimes you come across groundwater also. Groundwater also is there, and the water seeps inside the excavation also. So we need to see what all is there inside the earth and what is the properties of all these things. The practice involves application of principles of the soil mechanics and knowledge of engineering principles, formulas, construction techniques, and performance evaluation of civil engineering work influenced by earth material. So all these combination of all these things will lead us to the geotechnical engineering investigations. In what we come to know, what are the all the things related to this geotechnical engineering are a combination of all these things. Soil mechanics as well as engineering principles are also involved in this. The base upon which knowledge structure is built as geotechnical engineering is a thorough comprehension of the elements of geological environment, because basically what we want to know is what is the different in the environment. There are other geological other properties are also there. There are different rocks are also there, and different rocks possess different properties also. So we need to study different types of soils, their properties. We need to study different types of rocks, what are inside the earth, what are their properties, as well as groundwater, what is groundwater inside also. All these has to be seen. Now let us see what is foundation engineering. In a broad sense, foundation engineering is the art of selecting, designing, and constructing the elements that transfer the weight of structure to the underlying soil or rock. Basically, we need to see some structure which can take the load coming from the superstructure. From the superstructure, the load comes onto the substructure and then onto the foundation. So we want to come up with some structure which can resist all these loads and transfer that load in a linearly manner onto the soil or rock. The role of engineers to select the type of foundation, its design and supervision of construction. So basically what the engineer does is, depending on the soil type, he gives us a suggestion, and he decides foundation which what type has to be selected. Before the engineer can design a foundation intelligently, he must have a reasonably accurate conception of the physical properties and the arrangement of the underlying material. This requires detailed soil exploration. So basically, first, before knowing what type of soil is it and what are the different factors related to it, if that is not known, the engineer can't come up with a decision. He can't decide what type of foundation should be used. So it is very important, before coming up with any structure, we need to know what type of soil type is it. Then depending on that type, then we come up from different foundations. We have isolated footing as well, we have combined footings as well, we have wrapped foundation, mat foundation, pile foundation. All these different types of foundations are there, that is related to the type of soil. Let us see the general observation. Soil does not possess a unique or linear stress strain relationship. It does not have a unique linear strain relationship, whereas we see this linear stress strain relationship in the steel also we see. But here that soil doesn't possess this, because in soil also you have again different types of soil mixed also. Sometimes this also happens. Uh, Soil behavior depends up on the pressure, time, and environment. Soil at every location is essentially different. Just let us see, the power has gone here. Let me just let us continue with the class here. Sorry for the disturbance. The current was gone. So the soil does not possess a unique or a linear stress strain relationship, as I told you. Whereas we have in steel, we have a linear stress strain relationship. Same way that cannot be achieved here in soil. The soil behavior depends upon the pressure, time, and environment. So depending on the pressure coming onto that soil, there might be changes, and depending on the time also. What time, how is it placed, at daytime or a night time or summer time or a winter time, all this also play a different role here. Soil at every location is essentially different. As I had told you, soil is not proper everywhere. At different part, the soil changes also. Sometimes this happens. You must have come across some soil is so hard. You even like can't excavate it with manually also. You need some mechanical equipments also, like a bulldozer or anything. Sometimes the soil is so soft it just gets inside. So here there are different types of soils. Nearly in all the cases, the mass of soil involved is underground and cannot be seen entirely, but must be evaluated on the basis of small size samples obtained from isolated locations. So basically, we can't see what is inside. We can just take some samples and we can judge from those samples taken from different spots here. Most soils are very sensitive to disturbance from sampling, and thus the behavior measured by a lab test may unlikely be that of inside to soil. So sometimes what happens, the soil from the site, when it is removed from the site, it acts differently, whereas when it is tested in lab, it varies differently. So this differences, some differences also there here, but still these things have to be followed before finally or before deciding our foundation. The foundation engineer should possess the following information. He should know all these information before deciding what type of foundation we know. Knowledge of soil mechanics and background of theoretical analysis. He should know the knowledge of soil mechanics, how the soil reacts, how the properties of soils are, what are the different types of soils, and all this should be known by the engineer. Composition of actual soil strata in the field. Sometimes what happens, the soil doesn't have the desired qualities and properties. So at that time, what we come is we come up with some experiments wherein we try to compensate the soil, consolidate the soil, and get the desired strength required for the foundation to transfer the load. So even this is seen here. Necessary experience, precedents, what design have worked well, under what designs have worked under what condition, all this have to be seen. We basically, experience also matters here. because sometimes with different soils, different reaction takes place, different settlements takes place. So this comes up with experience only. So even this is very much important here. Engineering judgment or intuition to find solutions to problem. The design engineer should be experienced enough, as well as he should have a good judgment depending on the different load factors and the soil condition. He should be able to judge it enough in the future what can happen. All this should be known here. Definition of foundation: the lowest part of the structure is generally referred to as foundation. So of a building structure, the lowest part is the foundation on which the whole load is transferred. Function of foundation: to transfer load of the superstructure to the soil on which it is resting. So function of foundation: to transfer that load which comes onto the foundation to the soil. Requirements: a properly designed foundation is one that transfers the structural load throughout the soil without overstressing of soil, which can result in either excessive settlement or shear failure, both of which can damage the structure. Sometimes what happens, if the foundation is not designed properly, then there are chances of settlement of the whole structure. Either if settlements takes place, or sometimes shear failure takes place, base shear failure takes place. The base moves away. Basically, this moves away because of the friction and the lateral forces coming onto this structure and the soil. So it is very important the foundation should be designed very properly here. Classification of foundation: you can see a shallow foundations and deep foundation. They are classified in two types. Shallow foundations are located just below the lowest part of the superstructure. They support deep foundation extend considerably deeper into the earth. Shallow foundations are those foundations which are not that deep inside the earth, like they are just below the superstructure. That these are the shallow foundations. Whereas the deep foundation, you can see the load coming here, concentrated load. You can see the plan of the footing here. Plan you can see here. Basically, this is the type of footing, and this is the in the blue color, that is of a column there which is to be erected. Elevation side, you can see this is the footing, and this is how the column comes in between, and this is the load coming from the column. That is the concentrated load coming from the column, from the slab to the beam, from the beam to the column, from the column to the footing, to the foundation. You can see that is the concentrated load, and this is how the load is distributed on the foundation. You can see a combined footing, combined rectangular footing elevation. You can see this is how a rectangular footing is placed here. You can see that blue marks, the blue squares are the columns which are resting onto the foundation or the footing here. Okay, this is how it is. These are the shallow foundations. You can see here you have combined trapezoidal footing also in a trapezoidal way. You learn about it in the further subjects. You can see the plan of elevation wall footing. This is the type of wall footing. You can see a whole footing is like a wall. You can just see it here. This is the footing. This basically this type of footing comes up where in the places where you have retaining walls also. At those places you have counterfort footing, as well as you have cantilever footing also there. This type of footings come at those places where we want to have a retaining wall to resist the lateral load of soil falling onto the structure. So this retaining wall resists this load. You can see a raft foundation. Raft foundation is basically is a whole mat type where the whole area is excavated, and that whole area of large footing is placed, and onto that the loads of the columns come. You can see this is how the raft foundations are. Now, what are the different loads on the foundation? This dead load refers to the overall weight of the structure. It includes weight of the materials permanently attached to the structure, such as flooring and fixed service equipment such as air conditioning. So dead load, basically it is the load self weight of the structure also, and different loads which are fixed onto the structure. Live load refers to the weight of the applied body that are not permanent parts of the structure. Basically, dead load is a permanent load and live load is not a permanent load. It differs. Permanent part applied to the structure during part of its usual life. Example: a people warehouse, whatever goods may move with time, and the people keep moving. This is the live load. Wind loads acts on all exposed part of the structure, calculated using building code. So wind loads are lateral loads, and earthquake forces is also lateral loads. So basically dead load and live load, these are the actual loads, whereas the wind loads and earthquake forces are lateral loads here. These are the loads coming onto the foundation. Different loads, these come onto the foundation. Depth and location of foundation. Depth and location of foundation depends upon zone of significant volume changes in soil. So what is the volume changes in soil, how much volume has to be removed, and what it should be filled with? This will depend on the depth and the location of the foundation. Edges in structures and property line, you can see if your footing is onto the property line, even that matters, where you have to come up with a footing. Either you can place it onto the property line or you have to move it somewhere else. Even this matters. Groundwater, if there is some groundwater, then you will have to move your footing from that side and you have to relocate it at the other side where there is no groundwater problems. Sometimes there are some underground defects also there, some reactive materials are also there, which have to be checked before finalizing the footing also. Even this has to be seen. If this is not seen and the footing is not placed at the proper location, then there are chances of settlement as well as base shear also coming up there. Let us see here, zone of significant volume changes in soil. What does that mean? Clays have high plasticity, shrink and swell considerably on drying and wetting respectively. So this clays, they change considerably in drying and wetting also. Volume changes greatest near ground, decreases with increasing depth. Volume changes usually insignificant below a depth of 1.5 to 3 and does not occur below volume changes. So what happens as we go onto the deep inside, there are volume changes takes place. And what type of soil is there, then again matters. On top there might be some good soil, there might be good soil which have good properties, but bottom again then there might be some soil which is not good, which has a plasticity property like the clay. So even this should be seen here. Adjacent structures and property lines. Structures may be damaged by construction of new foundations as a result of vibrations, undermining by excavation or lowering of the water table. Sometimes this happens. After new foundations have become constructed, the new loads they place on the soil may cause settlement of previously existing structures as a result of new stress pattern in the surrounding soil. So even this happens if there are some other structure coming up, other elements coming up at the property line, then this might affect even your footings also, and there might be some settlements also. You can see a part extending the property line. You can see the property line with a marked line there, you can see, but our foundation or the footing is extending in the other's property also. Now just imagine when the other person goes for excavation, he sees your footing this side, then there are chances of he might cut that footing which has gone on to his property line. In general, deeper the foundation and closer to the old structure, greater will be potential for damage to old structures. So existing footing is there, a new footing is there. Existing footing is old enough and it is at the bottom place, but the new footing, there are because of this close positions, there are chances of damage to the old structure, old footings. So this has to be seen. Where is my location? Where am I placing the footing? Groundwater, presence of water reduces soil bearing capacity, larger footing size, more cost. During construction, pumping is necessary, adds to cost of construction. Now what happens, some places we have fixed the footing, we have fixed the column, we are not able to move it. At those places what we have to do is we'll have to remove the whole water. We have to go for a very large footing, large foundation, and we have to go for some other treatments where the footing can resist the load and transfer the load properly onto the soil. So it might increase the cost also. This happens, the cost increases. Underground defects, footing location affected by underground defects, faults. There are faults inside caves, are there, mines are there, sewer lines are moving, underground cables and utilities. If all these are moving from those places, then there might be problem with the footing. So underground defects are, these are the defects. So you can see the bearing capacity, modes of failure, strip footing in dense soil. So basically if there is dense soil, then we go for strip footing also. Sudden appearance of a clearly defined distinct failure shape. You can see a sudden, because of that there is a general shear failure also takes place. As the load increases, the settlement also increases. So all this has to be seen properly. So footing is a very important part of a structure. It takes the whole load of the structure and transfers it onto the soil. If the footing is not proper, then there are high chances of failure, there are high chances of damage to the structure, there are high chances of cracks. All this happens here because of improper placing of footing. So it is a very important topic. And then again we have different types of footing also in there. Now we have raft foundations, we have mat foundations also, pile foundations also. All this will be seen in the next coming classes. So it is very important. I request all of you all to please go to this. You can see here, strip footing is a relatively loose soil. Now where is it? You can see a local shear is there. When load reaches Q1, further settlement takes place with jerks. As the load is increasing, then further settlement is happening. You can see at QU, right side figure, you can see here, you can just see this figure here, QU. Well, here there is a settlement. As the load is increasing, again the settlement is coming up to here. At QQ1, no so distinct failure surface developed, does not reach ground surface. At Q, when the load is increased, at QU2, failure surface finally reaches ground surface, not distinct settlement, or more in this case a complete failure. So what happens till here? It is proper. There is no problem here. But after some more load is increased here, then what is happening here? The load is, because of the load, there is settlement this side. So strip footing, you can see here, relatively loose soil is there. Here there is loose soil, because of that this settlement is taking place, and that is a local shear failure which is happening here. So till here, I think, hope this was clear. And it is very important we should know different types of footings and foundations. If that is proper, then if this structure is proper, basically what happens while designing, we first design the slab, then we go up to the beams, and from there to the columns, and then to the footings. In design procedure, we start with the slab design, we end up with the footing, but while executing, we start with the footing foundation, and then we go up to the slab. So it is very important the foundations will be strong enough to take some accidental loading also, some unprecedented load, or some unestimated load also. When it comes, it should be able to take that. I hope this session was clear to you all. I request all of you all to please go to this session, and comment in the comment section. If you have any questions, I'll try to answer it to you. Thank you. Thanks a lot for this session.